Welcome to Lesson 10E, Degree Days. We're going to talk about degree days, which is a way to measure or estimate the cost of heating, and you can also do the cost of cooling. This applies only to makeup air, air that's either coming in through a recirculation system with forced makeup air or infiltration and exfiltration. For example, my house, I have a forced HVAC system, but there's no makeup air coming in through that. The only makeup air I get is infiltration and exfiltration. We always have this dilemma that we want to maximize this for indoor air quality, but we want to minimize it for cost because it costs to either heat or cool that air that you're bringing in. You get the best of both worlds if you use an energy recovery ventilation system, ERV. What we're going to do now is look at how to calculate the cost of whatever makeup air that you're bringing in, assuming that we don't have any kind of ERV that would recover some of that cost. In the HVAC industry, they use something called heating degree days, and they use the symbols either DDH, which is what we use in the book, or HDD, heating degree days, and something else called cooling degree days, as you might guess, DDC or CDD. And for a given location, say a city, we would calculate for one day the average outdoor temperature, and we call that T outdoor with a bar over it to mean an average. Let's pick a fall day in State College, so let's suppose that T outdoor is equal to 55 degrees F. And we'll also define T balance, the balance point temperature. We call it a balance because if T outdoor average, this outdoor average temperature for the day, is less than T balance, then we need heat. T balance is not necessarily what you keep your house temperature at, but it's a number that corresponds to that for an average house. When do you actually need heat? So if it's 66 degrees outside and your balance point is 65 degrees, you probably don't need heat. You generate enough heat just from your refrigerator running and lights, and you and your family. You might have the house set for 70 degrees. If this T outdoor bar is greater than T balance, then we assume we need cooling. The standard T bal, unfortunately, there's two different ones, either 60 degrees F or 65 degrees F. In our textbook, we adopted 65 degrees F. So I'll just make a comment here. Always use T bal equal 65 degree F in this class for any homework, quizzes, exams. Let's take our typical day, this example. So T balance minus T outdoor on this day would equal 65 minus 55, and those are in degree F, equal 10 degree F. We call this 10 heating degree days for this particular day. The units would be degree F times day. We want to sum this up over the whole year or over the whole heating season. So over a whole year, you simply add up all the heating degree days, like we did this just for one day. So we add those up, and we'll call that the heating degree days for a year. These are all per day. Let's define DDH equal HDD, heating degree days, equal one day times the sum over a year, 365 days, of T bal minus T outdoor, and that has a bar over the average, and put that in parentheses. And then we're going to put this little plus symbol here, and the units are degree F day or days. We're doing this in the English system, which is still used in the HVAC industry in the United States. We're not going to be converting things to metric. Temperature has been one of the most resistant parameters to change to metric. This plus means that you count only when that thing in parentheses there is positive. If you have negative, that's when you need cooling. Throughout the year, you'll get some positive values of T bal minus T outdoor. It's cold outside. And you'll get some negative values when it's hot outside, and they would just kind of cancel each other out. And you don't want that. You want to count only when you need heat. This is heating degree days. So in other words, we count only heat. By the way, we do this for a season rather than a calendar year. And the season is July 1st to June 30th. That makes sense because we're talking about a heating season. I'll give you an equation soon, but the main goal of this is that the heating cost is directly proportional to DDH. Now there's a similar thing for cooling. Cooling degree days equal DDC. We use that notation in our book. And it's the same equation, except we're going to use negative, but it's usually written just by switching the temperatures around and still putting a plus. So we're going to do it this way. 1 day. By the way, the reason this 1 day is here is to make the units come out right, because the units are going to be in degree F times day, so you have to put a day in. So 1 day times over 365 days. Now we're going to define it as T outdoor bar minus T balance. And again, we'll use a plus. So this is CDD or DDC. And the T-bal may or may not be the same as our 65 degrees when we're doing cooling. The difference is this is based on calendar year. So this is January 1 to December 31. So that's an actual calendar year. And that makes sense because you want to make sure you go through the whole summer cooling. Of course, this would be exactly opposite if you lived in Australia. Cooling cost is directly proportional to DDC with a slightly different equation. I'm going to only do heating in this course. I'm not going to talk about cooling. So let's look at some heating degree days and cooling degree days. Typically in State College, PA, which is where I live, the heating degree days is typically around 6,000. Remember, the units are degree F days. And DDC is typically around 600 to 800, depending on whether we have a cold or hot summer degree F days. So you see that heating in State College is a lot more expensive typically than cooling, and you have a lot more degree days to heat than to cool. There's a very good website to find these DDH and DDC at any city or zip code. Here's the link, weatherdatadepot.com. Let me go there. Here's the website, weatherdatadepot.com. The first thing you need to do is set this to 65 degrees. These are in degrees F. And then you pick your location. Put a comma between the city and the state. Pick your years. The default is 2019 and 2020. I'm going to make my base 2020 and my comparison year 2023. You have to hit Run Report to refresh it. In base year 2020, there were about 5,300 heating degree days and just under 1,000 cooling degree days. This is just the total. In 2023, since I'm recording this in September, we don't have data for the last 4 months. But just comparing through August, we had a warmer winter and a cooler summer. Notice how much bigger the heating degree days are than the cooling degree days in State College. Let's try a different city, like Atlanta, Georgia. The heating and cooling degree days are almost the same. Even further south, like Miami, Florida, there were only 88 heating degree days and over 5,000 cooling degree days. Let me summarize all these equations. Here's our equation for DDH, DDC, which I already gave you. And then here's the equation that we'll use for heating. This is in dollars per year. T-ref equals 65, but the building air is heated to 70. So if you heat to 68 in the winter, you'll save a little bit. This is one of these engineering equations, which I'm not a big fan of. You have to put everything in the correct units, and then you don't worry about units. You get your answer in dollars per year. DDH is degree F heating days based on a T-bal 65. So that's how this equation, this constant especially, is derived. T operating is the number of hours per week, and that's often 24/7, 7 times 24 hours per week. But if it's a business might only run their heating system during the day. C sub FU is the unit fuel cost, dollars per unit, and then QFU is the unit fuel energy, BTU per unit. And it's absolutely critical that these two units must be the same in QFU and CFU, otherwise the equation won't work. They have to cancel each other out, in other words. Notice that CFU is in the numerator, QFU is in the denominator. So as long as this unit in each of these is the same, you'll get the correct unit cancellation. And this unit can be anything related to the fuel. If you're heating with oil, it can be gallons. If you're heating with natural gas, it could be cubic feet or CCF. C means 100 cubic feet. If you have electric heat, it's kilowatt hour, etc. And then Q is the makeup air only, and that is in ACFM, actual cubic feet per minute. You can have QM from the forced makeup air plus Q infiltration. And then I'd copied some tables from the book for typical degree heating days. This is in metric system, but we're going to always use English system for this. And you can see different cities around the country. And then table 5.6 gives you available energy per unit of fuel. So this is what we're calling the QFU. And you can see that denominator. This is what we call unit, and like I said up here, it can be gallon, cubic feet, kilowatt hour. Here it's pound mass, gallon, cubic feet, kilowatt hour. These are actually old numbers. You can get some gas furnaces now with 95% efficiency, so they've come up quite a bit. And now let me just also add here, since these are much more popular these days, a heat pump with a coefficient of performance of 2.0, let's say. The efficiency is actually 200%. For each kilowatt hour that you spend in electricity, you get 2 kilowatt hours of heat. This gives you 6,830. There's a factor of 2. If you have a geothermal heat pump, which I have in my house, typical COP, these are year-round averages, say 3.0, which is 300%. So you multiply this number by 3 and you get 10,245. So in my house, every kilowatt hour I buy, I get 3 kilowatt hours on average of heat to my house. We're ready to do an example. Typical house in State College, 20,000 cubic feet is the volume. 0.5, 1/hour is the N due to infiltration. Homes heated by a heat pump with a COP of 2, 10 cents per kilowatt hour. Let's estimate the yearly heating cost for this house. Again, this is only for makeup air. It does not include losses through the walls, windows, radiation, convection, conduction. So the actual cost is going to be a lot higher than this. This is just for air that infiltrates into this home. This house, like my house, has no forced makeup air. So all we do is use this equation. That's our solution. We know that N equal Q over V by definition. So Q equal N times V. So here, there's no other makeup air. Normally you'd have QM plus Q infiltration, but QM is 0. So Q is equal to N infiltration times V. And so that's 0.50 1/hour times volume, 20,000 cubic feet. Watch your units as always, 1 hour is 60 minutes. So this gives me 166.67 CFM, ACFM. And then from the table, we have a COP 2.0 heat pump, which is a typical air-to-air heat pump that you see outside everybody's house these days. QFU I just showed you of 6830 BTU per kilowatt hour. Make sure you watch your units and convert everything into these units. CFU is the unit fuel cost, and I just told you in the problem statement that's $0.1 per kilowatt hour. And remember, these denominators in CFU and QFU must match. State College, PA, typical year around 6,000 degree F days. That's our DDH. T operating, this is a house, so we say 24/7. That's 24 hours times 7 days is 168 hours per week. It's actually a misnomer. It's not a time. It's a time per week. That's everything we need, so it's a matter of just plugging in this equation. So I just plugged in all the numbers without units, and you get 378.80. The units are dollars per year. If we round that off, we would say this is around $379 per year in heat. That seems really low for heating a whole house all winter. That's very logical, Mr. Kirchhoff, but that does not include any other heat loss, like heat loss through walls, windows, ceiling, radiation, etc. This is just makeup air cost. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. That's all there is to it.